Okay, let's have a small review. Consider this. We have a rectangular loop, something that looks like this, that's rotating about an axis that's passing through the center. We are having here a top view. Now this side is just below this point, and this side is below this point. At one time or another. Now, if this side, because of the rotation, is moving with a velocity v, then this other side, since it's halfway, is going to have the same velocity v. Now, the velocity v is related to what we call the angular frequency omega by this expression. V is equal to r omega. Now, that's when omega is expressed in radians per second and r is expressed in meters. We get a velocity in meters per second. Now remember again, omega is expressed in radians per second. Now the angular frequency omega is related to the regular frequency, what we determine how many something rotates per minute, through this expression. Regular frequency is just omega over 2 pi. And the regular frequency is expressed in rotations per second or oscillations per second if it is an oscillation. And that's hertz. The unit for frequency is hertz. And of course, the period of something is the inverse of the frequency, which would be 2 pi over omega. And the period is expressed in seconds, obviously. Okay, let's consider this. Now we have our loop that's actually rotating in a region where I have a magnetic field. It is shown here through the blue arrows. And the idea here is to consider the force experienced by each side, and that force is going to result on an EMF induced in each of that sides. Now, remember the EMF is given by this. If I have a bar, since it has charges within it, as it moves in a region where we have a magnetic field, there is going to be a change in electrical potential. That's change in electrical potential energy per unit charge. So it's going to be the work done on the charges over the charge. And that EMF is given by QVB sine theta times L over Q, which we kind of summarized as VB perpendicular L, or VB sine theta times L. Now remember, EMF is a voltage. So this is where we have this from. So side 1 is going to have an EMF given by that expression. In the same token, now if you try to apply the right-hand rule, like we did here, look at the right-hand rule here. We have the magnetic field coming out of the page. The velocity is towards the right. So when you use your thumb towards the right of the page, your fingers outside of the page, pointing perpendicular to the page, then you'll see that your palm is going to point down, saying we have the positive charges being pushed downwards, giving us a direction of the current in this direction. Now when we go here, now if we have a particular direction for the current in here, applying the same right-hand rule, we are going to have exactly the opposite direction for the current in segment 2. We have the same velocity, but then since it's in the opposite direction, we are going to have the current in the opposite direction. So now the other sides, the perpendicular sides, the top and the bottom, the EMF in them are going to cancel out, because whatever is going to be produced here is opposite to what's produced here. So overall, the only EMFs in the loop are going to be due to side 1 and side 2. And so they add up, and overall this is our EMF, VBL sine theta plus VBL sine theta. Now, however, if we replace V by omega times R, in both of these cases, that gives us this. Now, remember, if this is R, that means this side is twice R in width. And L, remember, it's referring to the length of the wire, which is in this case the length of that full side. Okay, the length of that side times this side, which is twice R, is the area of that loop. So that's why we can write here twice R times L is equal to A. Then the EMF in the loop is actually omega A times B times sine theta. And now what's theta? Theta is the angle that B is making with the velocity here, and that angle is going to depend on omega and on the time. So we can just write that angle as omega times t. So my expression becomes omega AB sine of omega t. And that's a sine function that's going to look like this. And that's the EMF generated when we rotate a loop, a conducting loop, in a region of constant magnetic field. Okay, let's try to visualize that here. Now, in this case, we are going to have a magnetic field pointing up. I'm going to remove it so we'll see things more clearly. And then this is our loop in gray here, and we are going to rotate it. So as we rotate it, you see the shadow of the loop that illustrates for us the magnetic flux in this case. Large magnetic flux getting smaller, getting larger, getting smaller, getting larger. And then we see as these tiny small arrows, they represent the current in the bars here. Now, of course, if I increase the velocity, we are going to see a bigger current, but then it's more difficult to monitor what's happening. Okay, now actually we can do that here. Put the pause and we do it in steps. So you notice the current on this side is opposite to the current on this side, and because of the EMFs, then we have the current in the other sides as well. Okay, now, so you see, and the current value changes as we go around. Okay, now pay attention to the sine function here. Now, when B is perpendicular to the area, when B is perpendicular to the area, we have zero EMF. We have a maximum EMF when B is parallel to the area. Okay? Remember what the angle is. The angle is between the side here. This is your loop. It's the angle between here and B. So when theta is 0, we have no EMF. When theta is 90 degrees, that's when we have the maximum EMF. Okay, this is theta is 90 degrees. Remember, theta is perpendicular to the loop, and this is a 0 theta. Okay. Now let's look at that in another. Okay, here we have the same kind of situation. We have a magnetic field pointing down, and we have a rectangular loop that's spinning about that region where we have a magnetic field. And as you'll see here, we have a current in here that's opposite in direction and the current in here. You notice that the current direction changes. Okay, now as the loop turns around, and then notice when the loop is perpendicular to the magnetic field, like here, the EMF that's shown here was 0, there again. And when the loop is parallel to the magnetic field, then we have maximum, like here, EMF, and then like here again, maximum EMF.